When it comes to choosing a transmission protocol, you have all options open, because DIGSI-4 supports all the commonly used protocol standards, and of course the very latest standard IEC 61850 in conjunction with Ethernet. This huge diversity means that problem-free data exchange is possible with both existing and future systems. Plug-in boards provide sufficient flexibility for the communication with an automation system. A multitude of SIEMENS 4 communication modules are available for you to choose from. They come in various optical and electrical versions and are therefore almost always compatible to the individual system configuration. With this, and in conjunction with different converters, you yourself define what your communication connections should look like. Whether wire connection, fiber optic, or even communication network. With SIEMENS 4, you send your data safely from A to B and back again. As soon as two or more devices communicate with each other, a common time base is indispensable. This is the prerequisite so that events can be correctly assigned and sorted according to their timely occurrence. SIEMENS 4 devices support different types of time synchronization for this. With DIGSI-4, you select and parameterize the procedure appropriate for your application. Suitable to the installed communications module, DIGSI-4 already makes a pre-selection. For an Ethernet module, for example, you will also find the Network Time Protocol, short NTP, in the selection list. This, by the way, is the only allowed time synchronization procedure if you use the IEC 61850 standard. With the rest of the parameters, you adapt the selected procedure to your requirements. The DIGSI Help gives you more information on time synchronization. Let us now demonstrate the numerous communication options available to you with a few examples. In the most elementary case, a SIEMENS 4 device is connected directly to a PC. You may also do this, for example, from your office, using a telephone connection in combination with a modem. If you wish to communicate with a number of SIEMENS 4 devices, you connect these with an RS485 bus. Alternatively, use a star coupler for this purpose. Of course, a SIEMENS 3 device or a device from the 600 series can also be integrated in this communication structure. And, thanks to Profibus DP and IEC 6870-5-103, it's also possible to connect a substation automation system, for example, CCAM. Communication via Ethernet with SIEMENS 4 devices version 4.6 and higher, and you're in business. Equipped with the new Ethernet interface EN100 and the latest DIGSI-4 version, directly connecting your PC with a protection device is now as easy as 1, 2, 3. Just specify an IP address in the device properties, select the usual method of establishing a connection, and before you know it, you're already communicating over a direct Ethernet connection. By using a switch, you can even communicate with several devices alternatively via one and the same PC, for example, also with your office computer that is integrated in your existing network. We saved the best for last. You communicate via Ethernet in conjunction with IEC 61850, putting you at the cutting edge of communication. As an example, you see a ring structure with two switches for the connection of PC and station automation. Optical EN100 modules with switch functionality are installed in the SIEMENS 4 devices. This saves you external switches for the individual devices. You'll find out more about Ethernet and IEC 61850 in the next films. IEC 61850 is the first and only standard that encompasses all the levels of switchgear. Individual users can communicate on the same level or between any other levels, all using the same protocol. The bus topology is highly flexible and can even be set up redundantly using a ring topology. The use of TCP/IP also allows to transmit other services, such as web services for remote maintenance, via the same communication network. The greatest advantages of IEC 61850, however, result from the standardization of functions, services, and the description language. This enables the seamless interoperability of vendor-independent IEDs. Independence from technological trends in system communication has to be one of the key requirements for a new standard. For this reason, IEC 61850 strictly separates data and services from communication technology more than any other protocol. The link creates a mapping of which the structure and syntax are also specified in IEC 61850. Envision this mapping as a driver for specific PC peripherals, such as a printer. When replacing the printer, you simply exchange the driver module. The rest of the system remains unchanged. In our case, this means all applications, all databases, and general communication functions can be used further on, even if there should be a change in communication technology. This ensures the long-term stability of the standard through many communication technologies. With IEC 61850, you can distribute functions arbitrarily to various different IEDs. For this purpose, the device-independent function units, so-called logical nodes, were defined. The application-specific functions are then put together using these nodes. Each logical node has interfaces for input data, output data, and for data required for configuration purposes. More than 90 such nodes are explicitly described in the IEC 61850 standard, which provides a broad basis for practically all requirements, including yours. Taking the example of a simple feeder, we would like to demonstrate how an application-specific function is designed from the stock of logical nodes. The replica of the two disconnectors, the circuit breaker, and one phase of the current and voltage transformer are each represented by a logical node. Together with the actual equipment, they represent the model of the primary equipment. In the model of the secondary equipment, CILO-type nodes check the interlocking conditions and, where applicable, issue a release for the CSWI-type nodes. These, in turn, will send the switching command to the disconnectors and the circuit breakers. The data of the transformer currents and voltages is relayed to the PDIS node. This node represents the distance protection and can also transmit switching commands to the circuit breakers. The standard groups logical nodes according to functional aspects in logical devices. In our example, control and protection. Further logical devices include measured value acquisition and fault recording. Logical devices are of course always embedded in real devices. For example, a SIEMENS multifunction device usually even contains several different logical devices. The point is, however, that the logical devices required for a complete application can be sensibly distributed over a number of different physical devices. And best of all, IEC 61850 compliant IEDs from different manufacturers can be combined in a single station and communicate with each other. The key to the vendor-independent exchange of configuration data is a standardized description language. For this purpose, SCL, the Substation Automation Configuration Description Language, was developed. SCL allows all relevant information to be written to a text file according to an XML-based defined structure. Each IEC 61850 compliant IED must now deploy this type of file, the so-called device description. This describes the configuration of the device, as well as its function and communication capabilities. Accordingly, the station description contains information about the network structure of a station, the assignment of the IEDs to primary equipment, and information about station internal communication. The station description is created using configuration software, the so-called system configurator. Needless to say that all information is also documented in SCL and can therefore be easily exchanged between different configuration tools. But how is station communication implemented? Meaning, how do the individual IEDs exchange information? Well, it's simple. Each logical node contains precisely defined data objects. For example, in the case of the XCBR node, this includes the function of the circuit breaker with its operating modes or the switch position. Using the system configurator, you can now link two data objects of different logical nodes, and your information exchange is successfully completed. Let's take a brief step back to 1976. As the first concepts for an Ethernet system were outlined, the sharing of printers by several users was very much the focus. Today, having cornered 90% of the market, Ethernet is the most common platform for communication between computers in a local area network, and thus the mainstream communication medium of our times. The fact that Ethernet offers a high level of backward and forward compatibility makes it all the more interesting with regard to protecting previous and future investment. This means that it's no problem to integrate a 10 megabit network into a today's 100 megabit network, which in turn will be easily integrated into tomorrow's 1 gigabit network. Another benefit is the simple and standardized cabling compared to parallel communication channels. As our example shows, you can even mix and match different conductor technologies. An optical fiber cable connects several intelligent data distributing units, so-called switches, using a ring topology. The IEDs in the control cabinets, however, will be connected to the individual switches via twisted pair cables. This way, a new IED can be added at any time, or an existing connection to the ring can be detached without permanently interrupting the communication. But how do the individual communicators talk to one another within a network? Quite simple. Each device has its own IP address through which it can be addressed by another communicator. IP addresses are written in decimal format in 4 blocks. Each block represents 8 bits. This results in a value range from 0 to 255 for each block. Since several networks can be connected via so-called routers, communicators from different networks can also communicate with one another. In order for this to work, each network also has an address. It is also included in the communicator IP address that we will now look at in binary format. The leading bits identify the network, the remaining bits address the communicator within the network. The information at which location in the IP address the separation is supplied by the net mask, a bit code that is exactly as long as the IP address. The principle is actually quite simple. All net mask bits set to 1 identify the corresponding bits of the IP address as the section that specifies the network. Similarly, the bits set to 0 identify the section that addresses the individual communicators. With this bit code, the router can extract the network section and thus assign the incoming data to the correct target network. Now let's take a closer look at several network structures. The star is probably the most frequently used topology for small networks. In the minimum version shown, at least one switch is needed that connects the 3 communicators with one another. You can, of course, connect several communicators to one switch. How many depends on the number of ports the switch has. For a larger, locally extended network, a ring structure is the better solution. A fiber optic cable should be given preference as the ring connection. The optic interfaces enable you to make connections over a distance of several kilometers. For the shorter distances, you then make the rest of the connections electrically. Or you basically decide for one continuous fiber optic cable, and in that way can dispense with external switches that would normally be assigned to the devices. The optic EN100 modules can transfer data via both ports simultaneously, and thus supply the switch functionality at the same time. That way, you really only need one external switch in order to connect the PC. If, however, you're very exacting about redundancy, then we recommend that you connect the PC to the network using 2 switches. Now let us show you 3 common configurations. In the first figure, you see probably the most frequently occurring topology. Several devices are connected to switches in the form of a star. These, in turn, are connected to each other via a ring. This ring is usually an optic design whereby patch cables make the electrical connection between the switches and the devices. This concept ensures a simple ring redundancy, while at the same time being low in hardware costs. Significantly more redundancy is offered by the second example. 2 optic rings, which are independent of one another, are connected to 2 switches. A double cable connects these switches with each other, and even the PC is redundantly connected. The expansion possibilities of such a topology are considerable. You may install up to 27 devices per ring. At the same time, you can also increase the number of rings if the switches used have sufficient ports. An alternative is the third example. Each ring may call 2 switches each its own. Even the PC is connected via its own switch. The ring is now realized with a double optic cable. One ring may once again connect a maximum of 27 devices to one another. Here as well, the number of rings can be adapted to meet your requirements. Ethernet and IEC 61850, no longer a problem with CPROTEC 4 devices, version 4.6 and higher, and the current DIGSI 4. In order to ease you quickly into the subject, we are going to show you an easy way of checking communications. We are assuming a configuration with 3 devices connected over Ethernet. If there are more than 2 users, you need a so-called switch. This is an intelligent data distributor, which also lets you integrate your PC with DIGSI 4 in the communication. The communication check begins by pressing the F1 key on device 1. The fact that LED 1 lights up on the same device confirms that it has been pressed. What's decisive, however, is that an indication is sent to the 2 other devices at the same time. An LED at each of the two devices respectively should then signal that they have received the indication. Pressing the F2 key on device 1 then deletes the indication and resets the LEDs on all devices. First, we need a project with 3 Cyprotec 4 devices that are suitable for communication over Ethernet and IEC 61850. As you've already done with all previous devices, simply select them from the device catalog and drag and drop them onto your project. For our example, we're going to select a 7SJ633 version 4.6. Similarly, the procedure for entering the order designation is basically the same. It's essential to ensure that you enter the correct system interface. To do this, select the setting Additional Protocols. This opens a dialog for additional data. In the top list box, select the setting Protocol. In the bottom list box, select IEC 61850 in the required interface variant. Close all dialog boxes and give the inserted device a name, for example, Device 1. Now follow the same procedure as before and insert 2 further devices in the project. As well as their name within the DIGSI project, each of the 3 devices also needs an IED name. This name will be used later to identify the user within the network. DIGSI Manager automatically specifies a unique name, which you can check in the properties of the devices, or, of course, assign your own name of up to 8 letters or numbers. Of course, you can also use devices that use other protocols for communication in the same project, and therefore in the same system. Using the pop-up menu, you can also insert the so-called IEC 61850 station quickly and easily in the project. This type of station comprises several devices that can communicate with each other over Ethernet according to IEC 61850, which is exactly what we want to show in our example. You can determine the specific devices you want to participate in the communication in the Properties dialog of the station. This dialog shows you all the devices available as potential users. It takes just a few mouse clicks to assign these to the station. The station element is your access to information on network connections and the data links between the various users. In the course of this topic, we will be showing you how to edit this information with the System Configurator. The aforementioned method of checking the communication requires the exchange of indications between the participating devices. Separately for each device, you define which indications are affected, what trips them, and where they are sent, using the DIGSI configuration matrix. We will show you how to do this again using our example Device 1. First, open the device by double-clicking the symbol in DIGSI Manager. In the dialog, make sure that the Offline option is checkmarked. Then click OK. This starts the DIGSI Device Editor. Click Masking I/O to open the configuration matrix. First, create a new information group. By grouping together all the indications that are required for communication, you will make them more clearly manageable. As with all other names in our example, you can assign a name of your choice to the group. However, for our information group here, we suggest you use COM-TEST. Drag the relevant indication type for the required indications from the information catalog and drop it onto the group button and give this newly created information a name. Now let's take a look at which indications are required for which device and how you need to route them. As soon as the F1 key on device 1 is pressed, we want an indication which we have called test signal to be transmitted over the system interface. We are also routing this as an unlatched indication to LED 1. This means that the LED lights up but only for as long as the indication is actually pending. Our requirement is that once F1 is pressed, the indication is permanently pending until the F2 key is pressed. In this case, a simple CFC function will help us. This will need to be configured in the course of this example. However, to prepare for this, we'll now insert two internal single indications in the COM test group and call them F1 on and F2 off. These two indications serve as input signals for the CFC function and are generated as soon as the respective function key is pressed. The result of the CFC function then decides the state of the indication test signal, meaning whether this indication is pending or not. The devices 2 and 3 receive the indication, also over the system interface, of course. Now, also route the unlatched indication to LED 1 for both these devices. Oh, and another tip on the different types of single indications. Please note that the information type internal single point indication is required for the indications F1 on and F2 off in device 1. For the indication test signal in the same device, you need to use the information type single point indication. However, the indication required in devices 2 and 3 is the type external single point indication. You have now almost finished the preparations for each individual user. You will be linking this information between the users later using the DIGSI system configurator. As this communication level is accessed by the functions model according to IEC 61850, all the Cyprotec indications routed to the system interface must be assigned to a corresponding IEC 61850 data object. To help you, DIGSI4 automatically opens a properties dialog as soon as you route information to the system interface. This dialog offers you an object that is already in the form of a complete path. You only have to specify the prefix. We recommend entering the same prefix for all users. While this is not mandatory, it tends to make things much clearer and more manageable. In our example, we have chosen the prefix ctest. Now save your entries and close the matrix. In order to ensure that pressing the F1 or F2 keys delivers a permanent on or off state, you now need to create a simple CFC function for device 1. We have already shown you the basics for working with the CFC editor. For this reason, we will only be showing you at this point which information you need to link in special cases. We can achieve this requirement using an RS flip-flop type block. Link the set input of the flip-flop with the information F1 on, whereas the reset input is linked to the information F2 off. This function is then completed by linking the output of the flip-flop and the indication test signal. Pressing the F1 key now causes the indication to be pending, and pressing the F2 key resets it. Compile the function and close the CFC editor. Once you've stored all items of information, close the DIGSI device editor and return to DIGSI Manager. Here you can now start the DIGSI system configurator. As usual, this can be done by simply double-clicking. When the IEC 61850 station is opened, you don't need to do anything further with regard to network structure. All three devices are already assigned to a subnetwork and have unique IP addresses. The devices are also easy to identify due to their DIGSI4 project names, which are shown as well as their IEC 61850 specific names. If you would like further details, please refer to the Properties window. This immediately provides the relevant information depending on the selected element. Now, switch to the Link area. For our example, assign the Goose application, available as standard, the name Communication Test. Now select source and destination objects for this application. These objects contain the information that you previously specified in the configuration matrix and have routed to the system interface. When looking for them, you can use these two clues. The prefix ctest, which we assign to each object in the device matrix, and the cProtect specific display text of the indication, which is also displayed. The indication test signal is to be sent from device 1 to devices 2 and 3. You first need to select the data object SPCSO1 for the user device 1. By clicking the Add Source button, the object is inserted in the source column of the interconnections window. Now select one after the other the destination objects for this interconnection. In this case, that would be SPCSO1 of both device 2 and device 3, and add these to the interconnections list. This is done by either double-clicking the data object or by simply dragging and dropping them to the relevant cell. This example also demonstrates very nicely that it's possible to assign several destination objects to a single source object. Now close the system configurator. A plausibility check is automatically carried out on your entries, which are then stored. Now update the parameter sets of the individual station users in DIGSI Manager. Now transmit the updated parameter sets to the 3 devices one after the other, and you are now completely ready for the communication test. CCAM PAS offers you a modular and scalable solution which can be optimally tailored for the task in hand. Whether it is for telecontrol, processing protection data, data gateways in the office world, or station control systems with automation tasks, CCAM PAS lets you get a grip on all your requirements and at the same time offers you a trend-setting system. Let's take a look at the basic package Full Server. This package provides you with all the tools you need to configure and parameterize your applications, archive configuration data and gather and distribute operating data, visualize process and system states during commissioning or output commands, monitor the status of applications, interfaces, and device connections, process and evaluate binary and analog values, and to be able to exchange data with other process visualization systems, for example. In the case of distributed systems, you only need the customized and more cost-effective DIP version for the individual distributed interface processors. And for those of you who prefer to parameterize and configure your system on a separate computer, we also offer CCAM PAS configuration as a separate module. The optional CCAM PAS CC provides an overview of all processes. The tried and tested SIEMENS WinCC forms the basis of this process visualization system. Additional modules optimize it for use together with SIEMENS PAS. Let's now show a few examples to demonstrate the wide range of system configuration options available to you. We will begin using a small application with up to 15 bay units. For this example, install both SIEMENS PAS and SIEMENS PAS-CC on a single station unit. For medium-sized to large applications with up to 100 bay units, expand the system by a separate computer for SIEMENS PAS-CC. Only SIEMENS PAS is installed on the station unit. Remarkably higher performance can be achieved using distributed system that can handle up to 150 bay units. Here, SIEMENS PAS operates with a full server and up to 6 DIPs. As previously, you can still operate and monitor all bay units with a single SIEMENS PAS-CC. By the way, this also works for several stations or independent plant sections. In the configuration shown, each plant section has its own SIEMENS station unit, which has SIEMENS PAS installed as a full server. The operating and monitoring functions are, of course, also redundantly configurable. To do this, you need 2 independent servers, each with SIEMENS PAS-CC installed. Additional clients support remote access to all data. For the majority of industrial applications, a simple system configuration is perfectly adequate. Our example shows an all-in-one system with a single SIEMENS PAS station unit that performs all incoming tasks. The station unit collects all required data from the connected IEDs. Communication with these IEDs is implemented, for example, via direct link, using the IEC T103 or Profibus FMS protocol. These protocols can also be used parallel to one another. New IEDs should preferably be connected to a station bus using the current IEC 61850 protocol. For the purpose of operator control and process monitoring in the station, install SIEMENS PAS-CC on the station unit and connect it directly to a monitor. Acquired data is forwarded to the process control center. If you are using a typical star topology, communication is implemented via IEC T101. Alternatively, you can also connect the station bus to an existing company network via router, in which case you should use IEC T104. Process information and fault data can be transmitted to a conventional office PC. This allows supervisors and electrical technicians to be kept up to date continuously. By adding evaluation programs, you can also ensure optimum post-examination of faults, thus enabling conclusions to be drawn with regard to future fault prevention. SIEMENS PAS points the way ahead. With an example, we will show you which route this path takes and demonstrate the step-by-step replacement of existing components with new ones. The initial state is a system configuration with a C0 LSA as central substation controller. CProtect 2 and CProtect 3 devices can be found in the individual fields. LSA control is implemented as station control. At first, you replace the existing central substation controller with a SIEMENS station unit. You can take the configuration data for the bay units from the existing parameterization. The old station control is replaced with a modern SIEMENS PAS-CC operator terminal. You import the required data from SIEMENS PAS. Existing IEDs are retained and connected to the SIEMENS PAS station unit using mini-star couplers or serial hubs. If required, you can expand the existing configuration with new IEDs. Select the protocol IEC 60870-5103, or even better, the newest standard IEC 61850 for communication with the SIEMENS PAS station unit. You can gradually replace old devices field by field with new ones to suit your requirements. Ideally, these would be directly connected to the CCOM station unit via Ethernet and IEC 61850.